Welcome, everybody. I'm really pleased today to introduce Dr. Stephen Greybush. Steve is associate professor at Penn State in the Department of Meteorology and Atmospheric Sciences, and also at Penn State, part of the Institute of Computational and Data Sciences. He got his PhD from University of Maryland. Outside of Penn State work, he's also associate director of Center for Advanced Data Assimilation and Predictability Techniques. And I think all that, weather, predictability, AI, we're gonna hear a lot more about that today. But I also wanted to mention that Steve's a member of the Consortium for Planetary and Exoplanetary Science and Technology. So Steve also works with Mars, which maybe we won't hear about today, but I would like to ask him about that over cookies. So Stephen, great to have you here. Take it away.
Thanks so much for the kind introduction, Gretchen. It's great to be here at NCAR. I made my first visit here as a student a while back, so it's great now back to be giving a talk today. So I'll be talking about two things today, snowstorm and severe weather predictability, and using the tools that are common to my research, Ensemble, data assimilation, as well as AI. So the ADAPT Center at Penn State looks at applying data assimilation to a wide variety of application areas. Looked at kind of snowstorms, which we'll be talking about today, and severe weather, but done some tropical cyclone work with Robert Nystrom, my former PhD student, now at NCAR. We've done the Mars atmosphere work, which is a talk for another day, but it's really been fun. And even renewable energy work in collaboration with NCAR as well. So the underlying tools, despite all these application areas, can have a lot of commonalities between them. And so I think that will be kind of one of the takeaways is, how do we use the numerical weather prediction and ensemble paradigm to help understand predictability of severe weather? And then how does AI fit into that picture as well? Okay, so Penn State is also now part of a consortium for data assimilation with a number of other universities, led by University of Oklahoma. So we'll be looking to also apply this knowledge more closely in operations. And there might be some opportunities on the education side that potentially could be with NCAR and others to help bring more people into the field of data assimilation. So hopefully this talk will also help to introduce kind of the topic through applications as well as a little bit of the underlying paradigms. Okay, so what is data assimilation? I was once asked by a student to try to explain it in maybe 30 seconds to a minute. So here's kind of my version of that. All right, so if we want better weather forecasts for the future, we need to know better the state of the atmosphere now. How do we do that? We combine observations with some first guess estimate to create an analysis. So how do we do that? We use Bayes' theorem. We're combining observations and this first guess. When we need to spread that information across different variables that we aren't measuring, and we need to spread that information in space to places that we are not measuring. And then finally, we use a dynamical model to let that information evolve in time. And through that, we can quantify the uncertainty of our estimate of the state of the atmosphere. Okay. So we use that routinely now, of course, in numerical weather prediction. So the idea is we start with the observations of the Earth system or whatever field we're studying, whether it's the Martian atmosphere or hydrology or winter storms. And once we have those initial conditions for our model, we run our models forward in time. And we know models, both our initial conditions and the models themselves, have uncertainties associated with those. And therefore, we look at the ensemble paradigm. Our goal is to get a sense of how confident are we in our forecast or reanalysis. Eventually, at some time in the future, we begin to lose predictability or knowledge of those initial conditions. So the underlying things is, how do we design a good data assimilation system? How do we design a good ensemble so that we're adequately representing that uncertainty or forecast confidence? And then finally, at what levels do we lose the predictability of the system? And what are the dynamics that are associated with those aspects in the particular case that we're looking at? And then finally, the AI revolution that has taken off, especially more recently, how does that fit into this paradigm, change this paradigm? So I'll kind of break down the talk into two parts. The first in which I'll look at winter storms applications, and motivate that, as well as look at some recent research from the NASA Impacts Field Campaign, and kind of get a survey of that. And then at the end, we'll look at some AI applications that's actually in collaboration with David John Gagne and NCAR and others in his group. Okay. So what we're looking at here are the kind of guiding science questions. Right? How far ahead can we skillfully forecast a weather phenomena? That's where the science meets society. So to do that, we're going to specifically look at winter storms. Right? What's the synoptic-scale evolution and mesoscale features? Right? They might have different limits of predictability and perhaps different limiting factors to that in the dynamics and physics. Okay, what do the ensembles reveal about these? And finally, if we're doing our own convection-allowing numerical weather prediction and data assimilation, can we better constrain the state of the atmosphere? What else can we do to improve predictions for these type of phenomena? Okay, so some motivation. I grew up loving snow, measuring it, living in the northeast part of the United States. So that sparked my interest in weather. So it's kind of fun to come back then as a faculty member, take the skills I learned in grad school at Maryland for data assimilation, and apply them to snowstorms. So looking at two cases kind of as a motivation to start this line of research. So here's two different storms, right? And heavily impacting the northeastern United States. In both cases, New York had a very wide range of scenarios for snow. In one case, which I'll show you, the city gets shut down over a forecast for 2 to 3 feet of snow, and only 1 foot happens. The second storm, very similar range in forecasts, and it sets a record in Central Park. So why do we have that great uncertainty in those forecasts, even a day or two out in advance? Okay. So that's going to kind of drive the motivating research here. So here's an example of an ensemble plume diagram. Each one of these is a different ensemble member. For this first storm, Boston, 25 to 40 inches, pretty high confidence forecast. And that did verify in that range for Boston. Here's the New York forecast. I remember sitting around with faculty colleagues and thinking, what do we do with a 5 to 40 inch range? Right? And I know that it's probably the case here in Denver, Boulder area as well. I think in the past few years, I've seen similar scenarios and maybe even higher amounts of snow than this in ensembles. Right? So first of all, is this realistic or not? And then if it is realistic, what is driving that uncertainty and how can we potentially reduce that? So to explore this, we made this new type of diagram called a predictability horizon diagram. So we want to look at how the ensemble spread changes over forecast initialization time. So I'm basically taking this plume and collapsing it down to here's the total amount of snow in a certain amount of time. This is from the models started at this lead time. And that way I can see as we get close to the storm, are the model spreads coming together toward the correct solution, as they did in Boston? Or are they staying far apart? Or are they going toward a solution that is not correct? Okay? And I'll explain the colors in a moment, but we'll see why the colors help us to explain kind of this evolution and spread. So you can see ensemble spread differs place to place, storm to storm. And hopefully it's matched with the errors of the day. Okay, so in this case, here's a 500 millibar chart, and we see a huge trough in the east. And the position of this surface low off the east coast of the United States was extremely important for this storm. So if we color-coded each of the positions of the low over here, right, some ensemble members close to the coast, some further out to sea, very small differences, maybe 50, 100 kilometers. But if you now color code here the approximate 1 foot of snow line, they're nicely matched here. And where do they pass through with about 50% probability? New York City. Okay, so given the amount of constraint of the initial conditions of the atmosphere about a day or two out, that range was reasonable for what the models, what we knew from our initial conditions and observing systems and what we can, how good our models are. Okay, so then what can we do? Can we trace this back in time and say, well, what could we have done better perhaps? So we have the ensemble sensitivity here. So you're color coding ensembles, you're rather color coding the 500 millibar field to show correlation with the east-west position of this low. So you can see strong correlation along where this trough is at 24 hours prior. If I was to show the 48 hours, the uncertainty would light up more strongly with this trough. And probably 72 hours, you'd back up even further. So that might say if we had better observations of the atmosphere in this trough location, that potentially could have given us better kind of position of that low pressure. And we see that really tight gradient. It even was borne out in the observations. Almost nothing just west of the city, a foot Central Park, and then you do get the 2 feet plus out in Long Island. Okay, so that's one source of the initial condition uncertainty impacting the synoptic scale. Okay, but that's not always as straightforward for other storms. So here is the 2016 storm. Okay, here is DC area. Confidence out almost 3 to 5, 7 days that there'd be a major event for snow. Ensemble showing 2, 3 feet of snow. That verified successfully at Dulles. Here's New York again. Right? So you'd expect, well, would it be down here? Well, this time it was near the top of the ensemble. So that's why you have to have that amount of spread. If that's all we can constrain the atmosphere based on our initial conditions and modeling, we want the spread to be that big. It's telling us to expect any of these scenarios. So communicating this type of information, we can think initial detection of a storm. When social media erupts, that one ensemble member is showing an extreme storm well in advance. But meteorologists know better. 2, the emergence of a signal. When does the ensemble mean shift toward the correct, hopefully, solution? To finally, convergence of solutions, hopefully around the correct one. Okay, we can also think, what about probabilistically? Do ensembles mean what they say when it comes to snow? So reliability diagrams, normally you want to repeat this across many different cases, but at least this is across many locations for this New York storm. Right? So this one-to-one line is showing that when you have 100% forecast probability of exceeding a threshold, at 100% of the locations it happens. So here it says that the ensembles are under-dispersive for a large amount of snow. Right? That's what under-dispersive means. The ensemble spread is actually not large enough. Because here you're saying there's a 100% forecast probability, but only 60% of those locations receive that amount of snow. So interesting, work to be done on the modeling side. Okay, so what do? We did some in-house modeling at convective-allowing scales for the storms. This is kind of a paintball plot of high reflectivity areas or where these intense mesoscale snow bands would be, because the story was more complex for this storm. If the snow band's set up over a particular region, you get 3+ inches an hour of snow, and that can make the big difference. So not just getting the low pressure, the synoptic scale detail, you also sometimes need to know the mesoscale details. And those mesoscale details have a shorter predictability horizon in some cases. So that makes an even greater challenge. Okay? So in addition to East Coast winter storms, we also worked with lake effect snow for the Owl's Field campaign. So we did ensemble data assimilation for that as well. This can kind of give a sample here, which I'll kind of dive into a little bit. So this is another example of very small mesoscale snow features. So over the Great Lakes, here's Buffalo, New York, and off of Lake Ontario, you can get extreme amounts of snow. I think there's records of 80 inches in a few days. And those that remember just, I think, December 23rd of just a year or two ago, 70-mile-an-hour winds and intense snow in Buffalo, really devastating storm. And so these are fed by the differences in temperature of a cold overlying air mass that passes over a relatively warm and moist lake. Okay, so what's going to drive the uncertainty in these predictions? Right? You can think about lake surface temperature and ice, things like that, but we also care about the synoptic scale details that are propagating from further away, and we care about some of the mesoscale details for these events. Okay, so here's an example case study that was studied by owls. We're looking at this band off of Lake Ontario and the Tug Hill of New York, and we're going to look at convection-allowing modeling over this region. Okay? And so here's just updating from just the boundary conditions, and this is updating using a regional data assimilation system. This thick black line is the observed snow band. So you can see how the data assimilation makes a difference if it's a short-term forecast. But going back in time, even with data assimilation, this band location, even though we know we're getting extreme lake effect, the exact location of the band is sensitive and was not forecasted well. Because you can imagine, if you lived here, the forecast was for nothing, but you may have gotten actually maybe a foot plus of snow. Okay, so what drives these types of errors? All right, well, we found that the synoptic scale error, this is information that's coming from outside the Great Lakes region, and here there's a fast wind flow, so you would have to get the synoptic scale details right for beyond 24 hours or so. Updating the model locally doesn't help that much because the information's coming from further away. Okay, that's the synoptic scale predictability part. But then the mesoscale details, maybe minute changes in wind direction, other things like that, can take place in the 1 to 24-hour time period. And then we also looked at multiphysics and other stochastically perturbed ensembles, and that also can make a difference, like what microphysics scheme you're using and things like that for kind of matching observations here. So that was a paper that kind of dived into some of those details. And here's an example of just how sensitive the band location can be. Okay, so here's different bands, and they're colored here by wind direction. So this is a wind from 255 degrees to 270 degrees. Very small wind direction change, and you can see how the whole band is going to shift. And that's why lake effect snow is so challenging. Right? We have to get the wind field down to that level of precision to try to get the location correct. Okay? So we also can see that you might want to treat these as objects rather than just pixel at pixel. Right? You want to know, well, even if the band isn't exactly right, did we get the right angle? How far was it off? Things like that. And you could also think about ensembles that if you had, let's say, a storm in many different locations, but none of them overlapping, the ensemble mean looks like a weak version of all of these rather than one strong one in the center. So working with my student John, we kind of tested out this idea of the geometric ensemble mean. And I'll show you what that looks like here in the results. Okay, so here's that idea of individual ensemble members not being kind of looking like this ring, but rather having a single member. And here's some examples of this for lake effect snow bands, right? Because we wouldn't want bands kind of having a wide brush area of weak snow. You want to know how intense will the snow be. So what would that ensemble mean look like in something like this? So you can think of this work here as kind of a prelude to the NASA Impacts work that's currently doing. So NASA Impacts is a field campaign over 2020, 22, and 23. And this was a coordinated campaign of 2 different aircraft targeting East Coast winter storms. So the ER2 flies high above the clouds and has radar looking down into the storm structure. And the idea is that this aircraft is flying overhead, and more slowly the underlying P3, this is like your Hurricane Hunter aircraft, is sampling the clouds underneath. So you're getting in-situ measurements of temperature and humidity, but you're also looking at the individual images of the ice crystals that you're sampling with the radar. Right? So this can help if we're then in the future using such measurements from space, how to calibrate them. Okay, so this is a good data set to help us further explore predictability, microphysics, other things that might be underlying forecast errors for snowstorms. So just to give a sample, this is the EXRAD radar looking down. This would be a cross section. So this is upward, and you can kind of see how the reflectivity increases as you get toward the ground in some of these heavier snow bands. Right, here's we got to be down at Wallops Island for a little bit on the ground side of things, flying into storms, mostly in Canada in 23, unfortunately, because East Coast was not as active in that year. Okay. So we're going to use this data to help us explore predictability. So what we're looking at here is a regional convection-allowing data assimilation system targeting the mid-Atlantic area with 30 to 60 ensemble members. Mostly set up similar to the high-resolution rapid refresh, but a smaller domain since we're at a university and have smaller computers for access. And we're going to assimilate conventional observations hourly, and then we're going to add in some field campaign observations in a future experiment. Okay, so just to give you a sense of what observations look like, and these are the dense ground observations we have from mesonets and other things. But if you're thinking about precipitation, we can't just know the temperature at the ground. We need to know the temperature aloft. So where do we get it? Well, we know we send weather balloons, but they're every maybe 12 hours at best, except in a field campaign, you probably have a few extra. And they're pretty spatially sped far apart. You're not going to get mesoscale details there. We do have commercial aircraft, but if an airport is closed in a snowstorm, probably not going to have many flights taking off and landing. So this is a major challenge if you're trying to get additional data for kind of this nowcasting or maybe short-term forecasting for storms. Let's say next 12 hours. Where is an intense snowband going to set up that the plows can't keep up anymore? Okay. So that's what we're going to try to look at. And I'm going to show field campaign assimilation, but also an idea that we're trying to explore for the future for this. Okay, so we'll start with the January 29, 30, 22 case. This is the one where the Doppler on wheels had a storm surge flooding around it because of the intense winds in the Boston area. So these are kind of our EXRAD observations. in the top row. And then at the bottom here, we have our WRF deterministic run. And then here's with our ensemble common filter, this is an ensemble average. So from the zoomed out back of the room view, we're capturing the main features of the storm, right, of heavy bands near the coast. But of course, the details are what's going to matter at particular locations. So how do we take a closer look and assess that? Well, a few ways we can do that. All right, so here's just an example of the storm. This is a 975 millibar low, so very intense nor'easter. And you can see this heavy snow band right here going right through Boston at the time. Okay? So we have 40 ensemble members. How do we summarize that without 40 individual plots? We can look at neighborhood ensemble probabilities greater than a threshold. So that's saying, well, maybe how many ensemble members are exceeding that threshold of, let's say, moderate snow. And so some of them have a band set up over interior Massachusetts, many more of them offshore. And one of the undergrads working with me, Jacob, took a closer look at this and was trying to look also and connect this to the microphysics a bit and try to look for areas of strong updrafts within the dendritic growth zone. So that's an area where dendrites, types of snow crystals, are typically formed. And so here's kind of a zoomed in look. There's where the base reflectivity radar was. You can see the max vertical velocities, sometimes in the areas of intense DBZ, and then taking a closer look here at where those kind of fields align, kind of in this box here. So the mesoscale details of the storm compared to observations, we have snow bands, but they're not always in the right locations, and we're looking to look next at ways that we can try to quantify that. So this work's kind of ongoing here. So if we had additional observations, how could we improve predictions? So this is a case from February 7, 2020. This was a more interior track, low pressure. Most of the heavy snow is in upstate New York here. And this is the flight of the P-3 aircraft from Wallops Island, Virginia, coming up here, doing a few passes through snowband, which I'll show in a moment. Right, so while this is passing through, we'll also have the EXRAD observations. So you're going to get wind retrievals, and you're also going to have the in-situ temperature and humidity observations from the aircraft that are available. Okay, so we're going to compare two runs, one assimilating that information and one without assimilating that information. Okay, so where are we going to focus on? So while the P-3 was flying up here, you can see the radar composite showing nice snow banding occurring in this area here. And we can confirm that with some New York mesonet observations. Here's the snow depth, and you can see February 7th from about 12, maybe 13 UTC to 18 UTC was nice rapid accumulation. So this is the time period of interest to look at. Okay, here's an example of kind of EXRAD observations of reflectivity. Now it's not an apples to apples because these are different radar types, but just to get a sense of where the heavy snow was, does it kind of line up in each of these? And then here's kind of a coarser resolution model. Okay, we can see the model's not perfect, but at least have some indications of banding in those areas, at least before the assimilation part. Okay, and now we're going to look at running some assimilation here, okay, just giving a sense of the synoptic-scale view of the storm from simulated reflectivity and satellite. Looked reasonable. So if we start with the quantitative kind of bigger domain analysis, so there's two curves. The air curve means aircraft plus conventional. Conv is just conventional. Okay, so comparing radars, that's something we don't assimilate. So it's kind of how do the temperature field and pressure and wind field and microphysics then lead to a different radar field in like an hour forecast. Okay, so we're seeing a little bit of improvement at the domain average, but does it match the statistically significance? That's showing more modest results on this part. But that's domain averaged. We're trying to zoom into the region of interest, and so that's where we're actively looking at the snowband region. Okay, so you can see right here in that part of upstate New York. So we're going to kind of first look at a few different comparisons across time. And what we're seeing here, so on the top is these are, again, neighborhood probabilities. This is with the impacts data and without the impacts data. And remember, the flights are kind of in this area. We're seeing increased probabilities of high DBZ, potentially indicative of snow banding in this area. Okay, that's encouraging because that's where the data is. And we can look at some difference plots. So positive differences in this area are showing the assimilation is increasing the reflectivity in these areas. So you can imagine that's an encouraging sign for the part we're looking at. We're less focused on kind of the squall line down here and other parts where we don't have additional data. So what could we do next? We can take a deeper dive. Okay, so here's again the air, the conventional, and the observations. The difference plot. And then what we're doing now is trying to come up with a feature-based approach that's specific to snowbands. So this is active work with my student John. And he's developed this kind of single linkage clustering-based algorithm to come up with band objects. Because once you have that, you can kind of do statistics on these snowband objects between two different images. Maybe even see how, using this algorithm, how one band object might morph into another band object and do kind of a feature-based diagnostic. And in addition, we want to kind of trace the updates to the wind field and temperature field and others and see kind of dynamically and physically how that impacts the radar reflectivity. So this part of the work's ongoing here. Okay. So there's more we can do though, because imagine we can't assimilate field campaign observations in an operational sense when there's no field campaign. But what might we be able to do? So what other source of vertical information about temperature regimes might we have? Well, if we think about dual pole radar, okay, so this is from Professor Matt Kumjian and Kelly Lombardo's paper, so he's a collaborator on this effort. There is the bright band feature that we see in ZH, and correlation coefficient, here's the melting layer, and here's another reduction in CC in the dendritic growth zone. So if we can find these fingerprints in radar, is there a way to extract those fingerprints that might tell us, well, we know here that this temperature is 0 or slightly above it where the melting layer is. And if the models aren't getting that at the right place, can we update them? Right? So if we can get a pseudo-observation from this, that's something we'd like to assimilate. But first, we have to better understand these fingerprints. So this is grad student Song Zhang, who's co-advised with Matt Kumjian as myself. She's exploring that. So that's kind of the motivation for this, is to eventually, hopefully, assimilate this type of feature. And others in the Penn State ADAPT group, Keenan Urey and others, have assimilated other kind of dual pole pseudo-observations. They've looked at ZH columns for severe weather, looked at also boundary layer measurements from radar as a pseudo-observation to update. So how can we do this? We're going to first try to co-locate the impacts in situ measurements with the radar beam. Okay, so we're looking for the closest radars over many cases over 2 different years of impact. So I think there's 9 different IOPs. And we're looking for, okay, once we found where the radar beam's impacting the flight track, what temperature measurement do we get from the aircraft? Okay, and then from that, we're now matching kind of the radar. I know it's a big volume, is scanning this location, which we have a temperature, we have a moisture, and we also have samples of what the cloud microphysics looks like, okay, and try to make sense of this. So Song put in a few different temperature zones from rain to melting layer, and specifically we'll be looking at the dendritic growth zone and the needle zone. Okay. So just to give an example on kind of the horizontal view, right, you can imagine overlaying the flight track with the radar. Right, and trying to get a sense of, do these features, for example, these reduced correlation coefficients, line up with unique temperature measurements here? Okay. So doing this systematically, we get these plots. So this is kind of a scatter plot of temperature versus radar, different dual pole variables. And then since we have a lot of overplotting, these are the box and whisker plots. So we're trying to see in the different temperature regimes, do we see different radar signals? Now, you have to know a few things in that going into the melting layer and rain layer can damage the instrument probe. So that was specifically avoided in impacts. So unfortunately, we don't have, for this purpose, a lot of melting layer kind of samples. So treat that one with a little grain of salt. But for the dendritic growth and needle zone, we have many nice examples for that. And so Song just defended her thesis and was looking specifically at kind of the details of the needle and DGZ. The story's a bit complex here, but I'll just give a little flavor of kind of some of these things. So here, this is a specific subset. Okay, this is DGZ aggregates with high ZH, and looking at the cloud particle images. So these are being sampled actually by the aircraft. You can see that there's many different types of snowflakes and even supercooled liquid water present in this temperature range. So you can see anything from aggregates, so snowflakes sticking together, to here's a nice example of a dendrite, to grapple and supercooled liquid water regimes, to kind of these irregular crystals. So with more time, I can kind of go in a little more depth with what she's seeing, but she's working to really kind of understand these details of the microphysics. And then once you kind of understand that, you might have more confidence in using these radar signals where they are clear about what's happening at the temperature range. Okay, so on the winter storms part, before I jump over to the AI part, what have we looked at? Well, we used these predictability horizon diagrams and ensemble sensitivity analysis and showed the predictability challenges with both East Coast winter storms and lake effect snow. And we also use these convection-allowing ensemble simulations of East Coast winter storms for understanding dynamics and microphysics. And if we're thinking about what's driving the uncertainty in winter storms, well, we have the synoptic-scale, the storm locations, we have the setup of mesoscale features and snowbands, we have what's going on in the microphysics and precipitation types. Many different challenges are driving winter storm predictability. And then we've also kind of thought about, well, what can we do to reduce that, right? Can we use unique signals from radar? We can think about the whole class of just improving data assimilation more generally. That's a topic that NCAR and Penn State and many others are thinking about. Is there room for AI to help us in improving predictability? So a lot of this impacts work here. You've gotten a nice sample of it, is kind of ongoing with a bunch of grad students in the group. Okay, for the second part of the talk then, I'll kind of transition over and taking this traditional paradigm of numerical weather prediction and thinking about the AI side of things. Okay, so I'm going to take this basic diagram and I'm going to gradually show some ways overall in the field that AI can be incorporated. Okay, so let's see this one. So here we have our data assimilation where we're inputting. We can think basically a lot of these can be summarized as inputs and outputs. So the observations are input to the data assimilation algorithm, and we get our analysis. We pass it a numerical weather prediction model that has parameterization schemes. The forecast from that gets fed through a forward model to simulate the observations, and they are compared, and then we update our field and keep iterating, and then eventually output our prediction. Okay, so a few of the data-driven paradigms we've been thinking about for years, right? So model output statistics or linear regression has been around for half a century or so, but we can think of that as data-driven post-processing. Right? We can do more sophisticated kind of machine learning schemes as a post-processor beyond linear regression, but that's kind of the idea, is having that red data-driven part on the outside. We could also think about uncertainty quantification. So here would be the idea that for ensembles, where you run multiple copies of the model, have different initial conditions, have maybe different stochastic tendencies in the model, or maybe you're even doing a post-processing correction to put a probability distribution around ensemble members. Okay, so you can do this without any machine learning. That's been done for many years, right? And you can also use data-driven approaches to help with this. Right? The analog ensemble work done here at NCAR kind of helps with the bias correction as well as kind of giving uncertainty estimates at the end from models. Okay? So that's another place to use AI. So you're going to see I'm going to keep putting the red boxes, the AI or data-driven parts, showing where they can fit in this paradigm here. Okay, then we can go to physical parameterization schemes. There's been work training physical parameterization schemes, let's say a radiative transfer model, to work much faster than a conventional one and help speed up modeling. Right? Hopefully it still generalizes well in other things. That's been done in our field. We can think about the data assimilation side. So there's work in looking at if you trying to model error covariances. If you have some samples with a very large number of ensembles, but you can only afford a smaller amount of ensembles in real time, can you learn machine learning-wise how to map from that noisy sample to a nicer sample? And you can think in machine learning, it's very common to go from kind of a grainy image to a nicer image, right? That's something that machine learning can do well. So you can also think about kind of the physical parameterizations here and using data assimilation to update the physical parameters. You can consider that some version of a data-driven approach. So Robert Nystrom did that as part of his PhD and postdoc. Okay, so here's that covariance modeling aspect. So John Harlem's work on that. I think others at NCAR and elsewhere are exploring that interesting way to do things. We can think about taking a forward model and replacing that with a machine learning model. That can speed up our data assimilation aspect. And then we can think of kind of some of the more revolutionary ways. So just 2 years ago, right, we now have replacements for numerical weather prediction models, like the one that the European Center is running and is being developed in many other places. Okay, so in this case, we still have a data assimilation scheme, at least to first generate the training data for this model. And then later on, you're still giving the initial conditions to this model that went through a data assimilation scheme. Right? But then you can take this, and people are probably thinking about ensembles of these, uncertainty quantification, and of course, careful verification is needed to see what aspects of forecast can be handled well and what are a challenge for these. Right? But this is something that maybe many thought was not as feasible 5, 10 years ago, but now is there, and in some metrics is outperforming traditional models. Okay? And then what about, do we need a data assimilation scheme? Right? So there's many ways to look at hybrids of data assimilation with machine learning. That's an interesting topic that you could think about. But you can think in the nowcasting sense. When you're doing data assimilation to spin up a model, there's this model spin-up issue, there's some other challenges, but in nowcasting, you can go right from observations to some type of prediction model to get an output. So the example I'm going to show for here that we've worked on with David John Gagnier and my student Da Fan is looking at convection initiation nowcasting without kind of a NWP-DA framework. It's taking satellite data, trying to figure out where new convections can occur, and then making a prediction. So that's what you need to do, is to train it. You need to give it a bunch of observations and outputs pairings, 100,000 of them or so, and then train the AI model, tune the hyperparameters, right? Test it on independent data sets, and then understand it. Right? How does it do well? Where does it do well? But then can you explain what it's looking at? That's even more interesting. And can you quantify the uncertainty in that? Okay. And eventually, this is kind of, we took the model out of the picture here, but you can imagine that in the future, a hybrid of a modeling and machine learning might be a really good way to go, because other work in the ADAPT Center here is focused on assimilating IR satellite information and improving convection. So this is Keenan Ure's work from Penn State. Okay, so that's kind of in the future path for this problem. Okay, so taking a look at this example here for convection initiation. Right? So we know convection can lead to severe weather, hail, tornadoes, damaging winds, flash flooding. And the challenge is, where is a new cell going to pop up that's not just tracking past an existing cell? Right? Probably many of us are good at radar extrapolation for an existing storm, but when is a new one going to pop up that's not yet on radar? Thankfully, we have the latest generation GO satellite that has rapid updating capabilities, high resolution. Right? So when do we see, when we're just in the growing convection stage before we reach the CI threshold and maybe detect that earlier? And then how do we deal with challenges, right? We have to be careful of too high of a false alarm ratio, careful of missing too many events. We have a challenge with spin-up if we're trying to do the modeling approach, right? We have challenges with cirrus contamination where we can't see under the cirrus clouds to where new clouds are forming. So it's a challenging problem to look at. Okay, so how do we do this? First, we need to define CI because we're going to give our training data to the model. And we need to have every example CI or no CI. Okay, so we're going to define CI from Colbert et al. 2019's definition. Radar reflectivity greater than 35 dBz. But specifically, we don't care about kind of just getting in the path of the storm correct. We want to find cells that are new. So we're going to exclude points that did not have high reflectivity in the preceding time period. Okay, and then we track storms. So this is an example of the storm tracking. So as a new storm is considered CI, it's then tracked and get a number. So right here, you can see how that started from just kind of very low reflectivity, grows, and then right here hits the threshold and begins to be tracked. So that's what we're trying to predict. We're trying to predict a probability of CI, and then the answer is either a yes or a no. Okay, so to generate the training data, we look over June and July of 2020 for our training and validation data sets, and then a testing from a completely different year, 21. And we're going to make this challenging. We're going to actually try to have a balanced data set. We have almost 100,000 examples. About half of them are the CI class. So that would be an example from here, these red dots. These are all new, these would be CI. Okay, then near misses, rather than just picking a lot of sunny day cases that are easy to differentiate, we're going to pick our near misses near the convection, but where convection doesn't happen. So if you compare our work to maybe others, if you're just looking at clear sky, the numbers might look lower, but we're intentionally making it challenging because forecasters have to deal with this challenge. Okay, and then we have some random parts of the data set, but a small portion that are going to be sampled just from random locations. Okay, so the next step here then is we're going to, around each CI point, we're going to extract a local satellite patch. So this is an example of, for example, an IR satellite patch. So specifically, deep learning can use the spatial information in this patch, looking for patterns. Okay, so we're going to look at 7 different channels in kind of the IR water vapor bands of GOES. And that's going to be our predictand. Okay, so we're learning how to match satellite images at 10 minutes or 20 minutes or 30 minutes prior to a yes or no CI. That's what we're being asked to do. Okay, so what does the deep learning architecture look like? So when I teach this, I like to start from linear regression and just add complexity until we get to this at the bottom, which is what we're using. Okay, so linear regression, y equals ax plus b, right? And then add multiple variables to that. If you add a nonlinear activation function, okay, then you now have logistic regression, meaning so all of a sudden you get to the threshold, it flips from being a low number to a high number. Okay, you take logistic regression, and now you add multiple nodes to that, so multiple kind of equations that are going to feed together. We now have a simple neural network. So now we went from kind of 1970s in our field to maybe 1990s in our field. Okay, from neural network, and we add multiple layers, usually a lot of layers, we get deep learning. So now we're to the 2000s in our field. Okay, and then deep learning is stacking, it's basically still inputs going into these nonlinear regression kind of levels and kind of feeding in all the way to get an output. Okay, so what we're going to do here, you can imagine that if we had to take a neural net and we're mapping every pixel on here, we'd have 48 by 48 pixels. That's going to be too many connections. The problem's going to be under constraint. So what we need to do then is reduce the complexity of that. And we also care about local patterns in the image. So a partial connectivity network gives us a convolutional neural network. So there we look at what's locally happening in the satellite image. For example, here, where is this gradient? That would then be a kind of a local information that gets propagated along and can be helpful for looking for patterns. Right? And then finally, the specific architecture we're using here that has these many deep layers. You can see kind of a schematic diagram, as well as these skip-ahead connections. That's allowing information from early in the process to propagate forward later. So maybe these early layers are looking for where's some vertical linear structures or diagonal structures or gradients or then other more complex parts of the image. And then we eventually break it down to a single dense layer where now we just have 1,000 pieces of information describing everything we've learned so far. And then eventually we have to boil it down to a single number, a probability of yes or no. So the process of training in machine learning is going to learn the weights for everything here. Okay? And you have to give it enough examples and have good hyperparameters to guide that search for the optimal weights to be successful. Okay, so how did we do? So we're going to compare against a logistic regression that doesn't have spatial information as a baseline model. And you can see right? Superior area under the curve, CSI, false alarm rate, Brier skill score, and things like that, right? So all these statistics coming from our basic kind of hits, misses, false alarms, and correct nulls. If we look at performance as a function of lead time, I thought it was really interesting how it follows this exponential decay here pretty nicely. So at 10 minutes, we have a reasonable scale. As we're going out towards 60 minutes, the scale is decreasing. So why is the scale going to decrease? So you can think about the initial condition predictability problem. We can also think that we're looking at local patches. So maybe at 60 minutes, the information we need is not local. And we could also think if we're looking at cloud development timescales, what's the timescale for convection lifescale? Right? Maybe about 60 minutes for some of the shorter-lived cells. So there's a bunch of reasons why the predictability is decreasing at about this rate. So I think further investigations of the predictability timescales and comparisons to modeling studies would be, with traditional NWP, would be very interesting. And we can look at performance diagrams. So in the rock curve, the further the curve is to the upper left of the diagram, the better the performance. So we can again see our ResNet model outperforming the logistic model, and the performance is getting worse as you get to longer and longer lead times. We could look at the reliability diagrams to see when the forecast probability is high, does it actually usually occur most of the time? And they're reasonably well calibrated as far as the reliability diagrams. And then I think this is where it now gets interesting, is to try to understand it more kind of at the dynamics and radiative transfer level. Okay, so what we're going to look at here, the bottom row is the radar field. Okay, so this is time, 0 to minus 60. So here's CI, we hit 35 dBz. If we go back 20 minutes, we have enough hydrometeors in the cloud. If you go back 30 minutes, it's not showing up on radar because we probably haven't generated rain yet. But if we go back 30 minutes and we look at the satellite image, we see a cloud top. It's not extremely cool yet, but it's noticeable. We see moisture pooling if we're looking in the water vapor channels. So as a forecaster, if we had this information, we'd want to be able to exploit that. So we're hoping that the machine learning is also focused on these features. Okay, so we need to know, right, what's the machine learning algorithm looking at? And for simpler machine learning algorithms like a decision tree or something like that, you can follow the branch structure. If this, do that. But for deep learning, you saw just how many weights. There's going to be thousands of weights that have to be tuned. So it's not very transparent from the structure of the model itself. So there's explainable AI that can look at the post-processed version of the AI and do sensitivity studies to understand what aspects of the image might it be focusing on to make a prediction. Okay, so there's a bunch of different types of explainable AI. It's a booming field, and NCAR is one of the leads, I think, in meteorology for using this. So for like a bird example, right, where might the algorithm be focused on? Is it the gradient around the edge of the bird? Is it the eye and the beak? Right? It's nothing encoded in there says this is what a bird looks like, follow these rules, but in the weights, the rules are implicitly encoded. Okay, so specifically, we're going to look at the partition SHAP model method here. And this is kind of a game theory approach. So we're going to imagine you have a baseline image. Maybe that would be an image without a bird, and then the image here. Okay? And we're going to say, from here, we're going to group pixels into superpixels, because we don't want to do that at every little dot here. We want to look over maybe a region that's a little more coarse. And from there, we want to know how can the contributions to the change in prediction be distributed among these locations. So in the prediction from no CI in the baseline to CI in our example, what specific areas of the image were contributing to that change in prediction, and by how much? It's an additive measure. Okay? So let's take a look what that would look like. So we're going to start with our 3 baselines here. So the first one, this is the more complex one. This is a 0.5 probability composite. So if we took a bunch of examples where it was equally likely that there's CI and no CI, this is what these fields might look like in the 7 satellite channels. Okay, and then the question we'd ask here is, well, what's different in the case where we do have good, correct hits compared to that? But maybe this is complex, so why not say, well, what if it was just a similar day to today but dry? So this is taking the maximum value of the satellite brightness temperature in this channel, as if it was like the surrounding dry air, and saying what's different between the prediction of these cases compared to that. Or maybe we even do an extreme, the channel max across many different images. Okay? So then what we look at, this is now an example. This is, I believe, a composite over 100 cases of correct hits. So we've done this in our paper of a bunch of different types where what does it look like for false alarms and correct nulls and everything else. But this is a look at the hits. You can see here the convection is kind of, so in the center we see cool cloud top temperatures in all the channels here, and water vapor pooling in the center of the image. Okay, then what we can do is we can tally up the SHAP values. These are additive, so if we add these all up, that's going to help explain the percentage prediction difference between, let's say, like our 0.5, and then in this case, these are probably like maybe 98% chance of CI kind of examples. Okay? And then that tells us what channels, right? Here's the 7.3 micron brightness temperature. All right, here's the 11.2 micron brightness temperature. Those seem to be standing out. And then we can see what areas. Okay? What areas are showing a positive contribution are in the warm contours. What areas are having a negative contribution are in the cold contours. All right? So we can look at a few different examples here. I'll jump down to this one because it's, I think, a little easier to read. So in the 10.3 micron brightness temperature, positive contributions from these cold cloud top temperatures right in the center of the image. Okay? Some of the others are a little more complex. It looks like in this channel, it's almost looking a bit at the gradient of the image here, right? Because there's these positive and negative contributions near one another, right? Sometimes it looks like, why is it having opposite signs? Well, you can imagine that these are channels that aren't completely independent information. So that's one challenge for interpreting some of these, is the independence of these different predictors here, right? These are brightness temperature bands, the low-level water vapor, mid-level water vapor, and others are correlated. They're not completely independent information. But it's kind of showing us that it's focused in the center and probably looks like on maybe biased to the left side here, looking for gradients. So next we can take a look at uncertainty quantification. So here would be kind of examples of where we're getting a probability. How often is this probability correct? So, right, so this is just a short animation, but you're going to want to do this systematically throughout the cases. Right? And so we can think ensembles might be an appropriate way to do this as well. So there's a bunch of ways to design ensembles for machine learning systems, just as there's many ways to design them for NWP systems. Right? We can start with different initial weights. And that way we might end up in maybe different local minima as we're training our AI system. We can look at Monte Carlo dropout, where we just take out some of the neurons here instead of letting them actually filter the path here, and that's going to add some stochastic noise to the process. And there's actually Bayesian neural networks where the weights are not a single number, but a distribution. You could assume they're normal, or even just relax that assumption. So many different ways to think about uncertainty in deep learning. So my student Don, David John, and others are working on this at the moment for this convection initiation, and kind of thinking how to illustrate kind of the deterministic approach, the ResNet, it's a single probability number, versus kind of the Monte Carlo dropout, where you're adding kind of noise to the model, to kind of a Bayesian approach, where the weights are kind of Gaussian, exploring this part of the hypothesis space, to this a Bayesian moped, where you almost like have a prior, where you start with weights from your deterministic and then try to sample the neighboring regions to come up with things. To the deep ensembles here, where you're varying the initial weights, so you might end up with different solutions and different local minima, and the deep ensemble plus MC. So he's actively kind of exploring these. Here's just a sample of comparing them on the Breyer skill score, but he's probably a few months you'll see some much deeper results on a lot of the results that he's doing right now, with a few different important questions. Composing uncertainty into the epistemic and aleatoric components, so data-driven versus model-driven uncertainty. Right? Can you explain the uncertainty with explainable AI? He's looked into that. And then kind of how do we link to the physics and dynamics? Let's say you're looking at cloud top temperatures. Where is the uncertainty range higher at what temperatures? So that way, kind of, we don't have to think of the kind of machine learning approach separated from the physics and the dynamics that we love in meteorology, right? We're trying to use our physical understanding to dig deeper into what the machine learning is looking at And I think a synergy of these approaches is going to help us be successful with that. So for future directions, we demonstrated deep learning with superior performance to a classic approach and used some explainable AI. And we're trying to look kind of big picture at ensemble approaches, uncertainty quantification, explainability of the outputs and results, thinking about hybridization with NWP and MWP ML approaches, and think about how this all fits together in that predictability paradigm that we're putting together. Okay, thanks. I enjoyed presenting today and happy to take any questions.
Yeah, thanks very much, Steve. I will take questions. I can start it off. So I want to go back to snow. So remember back when the first talk. You showed an example where we were bringing in observations from the P3 and assimilating them and looking at how that improved their performance in some ways. You also mentioned, let's ignore places away from that because that's not where we assimilated data. But there were clearly changes happening, not surprisingly. You're going to put in some sort of signal, that's the way models work. You're going to see also changes in the solution in other spots away from that space.
Yes.
Have you spent some time looking away? Because I think we also want to know if you're bringing in focused observations, how's that locally impact the forecast, but also how's that non-locally affecting the forecast?
Yes, that's a great question. Because thinking about research to operations, right? You can develop something that's very targeted to improve a specific feature, but if it degrades something else, that's not good. Now, in these cases, I don't know that degrade would be the right word. Let's say you have convection elsewhere, and those updates eventually in a few hours propagate, and the convection gets shifted a little bit. Both of them, maybe no one's not more right or wrong. We'd have to do a careful validation of that feature. And then think, how does information propagate? Does it get lost out by the synoptic-scale uncertainty and not matter after 12 hours? Or does it kind of the butterfly effect where it grows over time? I think these are really interesting questions to dig deeper in on that. And I think that's a really important point to consider. Look in, but also keep the big picture in mind too.
For the convective initiation, essentially you're using clouds to predict clouds, but the clouds are there because of environmental forcing.
Yes.
Wouldn't it make more sense to associate the CI with the environmental forcings rather than something that's already a result of that environmental forcing?
Sure. So I think the future work with, let's say we're using her 15-minute fields, that's going to give at least, you can think you might have, let's say, your sounding information from the beginning of the day. You can use those as predictors. And then as you're getting closer to the time, do you have any of the mesoscale details in the model that can help you? Or are they poor enough that they might not help you as well? I think most of the time you should get value added from that next step. So I think, yes, you can include that. The nice thing about the satellite observations is they're rapidly updating, and the errors in those fields are probably going to be somewhat smaller as to the exact kind of locations of the features compared to, let's say, using a HER field as predictors. But I think adding that information is, in some sense, more fundamental and it should add value, and you should be able to find a machine learning system that is able to use that information for you successfully. Great idea.
So I have a question about the explainable AI.
Yes.
I agree, it's interesting to ask what is going on under the hood. But what do you do with information once you have it, once you've explained AI?
Yeah, that's a good question. So you can think about helping the AI to guide science. Now, sometimes you'll see, well, I expected it to look at this region, and it did. In some cases, will it tell you something new that you didn't expect? In some cases, will it tell you something about the training that is wrong? For example, the example of, let's say, animal classification, but it's looking at kind of the blue background in some of the images versus kind of it might be looking at the wrong part of the image that doesn't make meteorological sense. So then is there a way to then tune and change around what inputs you're giving? And from there, I think the dual goals of the science, can AI help you kind of look at some science questions and dig in just for the science sake? But then can the explainable AI help you design a better AI system? Because then it's not just, well, we have weights and we have to optimize them, but maybe there's some, even though we're trying to get away from feature engineering and other things with deep learning, there is still some feature engineering and hyperparameter optimization going on, and even design of the system that might play into kind of thinking about that side of things.
Hello. Thanks for the talk. You said a lot about the uncertainty here. How about the bias? So you used like a satellite images here to train your ML or DL, whatever. But usually they are known to like be biased. And then in the DA, without bias correction, they are almost useless, right?
Yeah.
So they are not perfect. Any input data would be perfect here. So how would you deal with that? And actually, on top of that, I mean, related to that, so you talked about the algorithms and the post-processing. But in DA, actually, pre-processing is more important, I can say. And in that sense, for the ML application, how would you way in that, or how would you do that?
Great question. So thinking about bias, the nice thing about machine learning is that if you have the input to output matching, you can do bias correction because the linear regression and then more complex model setup has kind of your y-intercept in it. But you have, of course, case-dependent biases and much more complex biases. So I think designing verification schemes to carefully look at kind of case-dependent biases is important. I agree with you with the pre-processing. I think much more work was done kind of to create this data set and think about it. So for example, parallax error. If we didn't correct for that, that was, at first it almost seems, well, why the radar and satellite images not even matching up? Now, the interesting thing is machine learning could probably deal with that. It would just think that cool cloud tops up here means the storm's going to form down here. It might be ignorant of the bias, but it could kind of learn around it. But is it better to have the parallax correction with that, where now you kind of are doing it in the correct way and then the explainability part's improved? Yes. So I agree. And the other interesting part is a lot of machine learning just assumes that your training data is perfect. And data assimilation, that's the biggest source of uncertainty. So I think in the big paradigm sense, I'd like to see more of that kind of brought into kind of how we use machine learning in meteorology, because that initial condition uncertainty is so important in the DA side that I think it just needs to be dealt with better on the machine learning side. Yeah, great questions.
Yeah, so we've already hit the top of the hour. I'm going to say Steve will be around for some discussion afterwards and more cookies. And also will be around tomorrow as well. So if you would like to follow up, please catch Steve and get on his calendar for tomorrow. Let's thank Steve one more time for an awesome talk. Thank you.